Hi, in this video I'll give an example of how to integrate the product of sine up to a power times cosine up to a power when at least one of the exponents is odd. Both can be odd as well, but at least one should be odd for this method to work. It's a very simple method. So I will show the case when, in this example, n is odd, when the exponent of cosine is odd. And for this example, it won't matter whether the cosine of sine m is even or odd. The method is the same as long as n is odd. If m is odd, you just do the same method, but you switch sine and cosine. And if both are odd, you can choose which of these two methods if you want to focus on cosine or sine. It's a simple substitution method. So since n is odd, we can replace it with n equals 2k plus 1, where k is assumed to be greater than or equal to 1. So we rewrite our integral, replacing n with 2k plus 1. And now we just want to separate out, let me see if we get the laser pointer here to make it a little clearer. So all we've done is replace the n with 2k plus 1, since we've said it's an odd number. And we're just going to separate this out into cosine up to 2k times cosine. So we take this plus 1, which is just times cosine up to the first power. And we do that because we're going to do a simple substitution, and this is going to be what we're going to substitute our du there. This is why this is convenient. So this is where we started in the last slide. We just replaced n with 2k plus 1 because it's odd, and we just separate out the cosine here. Then we're going to rewrite this term here, cosine up to 2k, which is the same thing as cosine squared up to the k. Right? Simple exponent rules. When you raise a power to a power, you multiply them. So we can do that in reverse. So all we're doing is separating this out. So cosine to the 2k is the same thing as cosine squared raised to the k power. So that's the only thing we've done. We've just rewritten this term in this form. And the reason we're doing that, which I'll see soon, is because this cosine squared is very easy to rewrite in terms of sine, because we'd like to get everything in terms of sine except for this term here, which will become our du when we substitute, which is why this method is easy. So starting here, again, we bring that down. And all we do now is we substitute cosine squared for 1 minus sine squared. And that's just the simple trig identity, like the real basic trig identity. Cosine plus sine squared is equal to 1. So all we've done is substitute cosine squared for 1 minus sine squared. And it's still up to the k power. So that's the only change we've made now. And now, as you can see, everything's in terms of sine except for this term, and that's okay because when we do substitution, we're going to need this to be our du. So this is what we started with on the last slide. And so now we're going to make a simple substitution. We'll let u equal sine x. In that case, du is equal to cosine x. And once again, if right now we're assuming that n is odd, but if m was odd and you wanted to do this, we would do the same thing except with sine instead of cosine, and we change the sign in that case. We'd have an extra sign, just like we have an extra cosine, and the remaining signs would change into cosine. And then the difference also here, our u in that case would be cosine x, and du would be negative sine x. So that would be the difference. You'd have a negative term here that you would have to keep track of. So we just take this expression here, and all we're doing now is we're substituting with our u substitution. So sine up to the m becomes u up to the m. 1 minus sine squared becomes 1 minus u squared. Still up to the k. And then here, cosine x dx, which we have conveniently right here, becomes du. And basically we're done. This is a normal polynomial. I can't show you a general step here because we don't know what k is, but all you would do is just multiply this out. You would you could use the binomial theorem, for example, up to k, multiply that out, then you multiply every term by u to the m, and all you have is a basic polynomial in u, and that's very simple to integrate. You just use basic integration rules for polynomials. And then, after that's done, you just substitute u back to sine x, and you'd have some fractions times powers of sine. I'll go through now one concrete example to show you with actual exponents how to use this. So we could take as an example sine up to the 10th times cosine up to the 5th. So we rewrite that now. We peel off one of these cosines because we're going to want that to be our du later. So now it's cosine to the 4th times cosine x. And this is why we see why it has to be odd, because we want to peel one of them off to become our du, but we need an even number left so we can change it into sine. Or if we had done it the other way, that we could change sine to cosine. So we could change all these sines into cosine right now, but then we don't have a convenient du. So now it's convenient to make this du, but we need an even number left when we peel one of those off. So we bring this down. This is the same as that. And now we rewrite this in that form where we have cosine squared up to some power, because cosine squared is what we're going to use to change it to sine. And in this case, since it's cosine to the 4th, it's very simple. It's cosine squared to the 2nd power. So it's cosine squared squared. We haven't done anything with sine yet, and we still have this cosine we peeled off to save for our du later. And the only thing that would be different at this stage is if we had different numbers up here, it would be this exponent, and then this 2 out here would be different. So bringing this down again, and now all we do here is we write cosine squared is 1 minus sine squared. And that's still squared on the outside, is still there. Nothing else has changed. Bring that up. This is just copied over from the last slide. And now we do the simple substitution. U is equal to sine x, du is equal to cosine x dx. So this here, we bring this down and we just substitute in the u now. So this sine to the 10th becomes u to the 10th. 1 minus sine squared becomes 1 minus u squared. And we have squared on the outside of that as well. And then cosine x dx here is our du. So now we have that simple polynomial. But since now I've actually used numbers, I can multiply it out and give you a concrete example. So we bring that up to the next slide, and now all I've done is multiplied it out. You could 1 minus u squared times 1 minus u squared, of course, is 1 minus 2u squared plus u to the 4th. And then I multiplied each of those terms by u to the 10th. So the 1 times u to the 10th is u to the 10th. Minus 2u squared times u to the 10th is minus 2u to the 12th. And then u to the 4th times u to the 10th is u to the 14th, and then the du is still there. And as you can see, as I said before, this becomes a simple polynomial. So we just integrate that with simple polynomial rules. Increase the exponent and then divide by it. So we have 1/11th u to the 11th. Increase the exponent, divide by it. So minus 2/13 u to the 13. Increase the exponent and divide by it. 1 over 15 times u to the 15. And of course, it's an indefinite integral, so we have our plus our constant to be correct here. And the last step is just to change all the u's to sine. So all we do is we change them back to sine. So sine to the 1/11th sine to the 11th x minus 2/13 sine 13x plus 1/15 sine 15th x plus a constant. And we're done. That is the finished integral. You can test that. It's easy to test, for example, is to type this into, for example, Wolfram alpha and ask for the derivative of this. And of course, you should get that. Typing this in to integrate Wolfram alpha will not necessarily give you this, because there's many different forms this can be written in. And you might get a lot of different forms. You can, for example, factor out a sine up to the 11th here. You can find a common denominator and combine these term fractions as well. You can change some of the sign. If we factor out a sine to the 11th here, then we'll have even sign and even sign here. You can change those to cosine or sine. So there's very many. That's often the case with trig integration. Is there's quite a number of equivalent ways to get the answer to it. Anyway, this is one example. And that's all. Thank you. Hope that was helpful.